Hi, my name is Grace Fernandez, and this is my Oscillations Lab. A quick introduction, I'll go over the overview, equations, models, graph, brief overview of lab results. Introduction, the purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. The equations I used were Newton's second law to get me the velocity update formula as well as the position update formula. There is no net force, so the change in momentum is zero. Therefore, the velocity is constant. I use Hooke's law, and that was to find my spring force as well as my time oscillations. And then I use energy principle to find the energy in the system because it is equal to the work of the surroundings of the system. In my models, I use tracker. So as you can see above, that I set the origin on the top right to the X and Y axis. And it's at the point where it's connected. And then at the bottom is my glow script model of it working and correctly. Here's better pictures. So in the graph to the right, the red line represents the delta UG, which is the potential gravitational force, and the green line represents the delta U spring, which is the spring force potentially, and the blue line represents the change of energy, and the orange line represents the total energy. The blue line is change in kinetic energy. The x-axis is time, and the y-axis is measured in joules. These are my other graphs that have time and the x position and the y position. Although the x and y graphs lines are very similar, it can be seen that the observed data points vary slightly. This deviation is seen evenly throughout the data and is likely a result of human error. Primary information. So the system is the object connected to the spring, and the surroundings is everything around it, like the air. Motion starts at negative 0.118 and negative 0.6250 meters and travels with an initial velocity of 0, 0, 0. It has a mass of 0.402 kilograms, and the time that the video started where he let go of the object was 0.0238 seconds. In the experiment, the spring constant was 6.83 newtons per meter. This was calculated in the video period of oscillations equation. Through the tracker, I adjusted the x and y axis to the origin at the fixed point of attachment. I then corrected the distance scaling stick. It was 0.7 meters from the top to the bottom. I then marked the position in each frame to get accurate data. After the data was collected, I used it in an Excel sheet. The object starting position, as mentioned before, and then the ball position variable is set to the update formula, the position update formula, to get the correct calculations. Here's my code. I also added the calculations for kinetic energy, potential gravity, and potential spring force, and the total energy using the equations mentioned previously. Here's my code up before. You can see on the right where it calculates energy charges, and on the left you can see more energy charges and L hat and L. Conclusion. The graph below shows that the points of data are very close for the x, as well as the graph periods are very close to almost equal. There's a slight variation in the periods on the x graph, and then the data points for the y graph show that the spring did not go as high as predicted, as you can see on the right side. Possible areas. Some of the data deviancies were probably resulted from me hand selecting the points. The delta t also could have been smaller, so that would have made it more specific, but because it wasn't, that could have caused for error. They also could have been because of the forces from the surrounding area that we did not include. So for example, like air friction. And for the model of the system, is the energy principle satisfied? I said yes, because all of the components are covered. And then using the data you obtained in the tracker, make two separate estimates of oscillation periods. For the first one, I calculated it using the graphs I made with my tracker, and it was 0.103 seconds, which is most likely incorrect due to human error. And then my y position, I calculated and I used the time oscillation equation, which comes from Newton's second law, and I was able to come up with 1.524 seconds, which I double checked with one of the videos that we used, and it was the same as the one in the video. And that is it. Thank you so much.